Okay, Unit 5, Acids and Bases, IB Topic 8. This is a nice diagram showing the relationship between the hydrogen ion concentration and the hydroxide ion concentration. If they're equal, in the middle here, we have what's called a neutral solution. If we have in excess of hydrogen ions, it's acidic, and basic would be the hydroxide ion. I'll refer back to this diagram later on in the unit when we get to the pH scale. Okay, the first topic is theories of acids and bases. Arrhenius acids and bases. This is Svante Arrhenius, 1909. He won the Nobel Prize in chemistry. He's referred to as the father of physical chemistry. He's a pretty big guy in chemistry. It's pronounced Arrhenius. Arrhenius. He was Swedish. And his definition of an acid is any compound that releases a hydrogen ion when dissolved in water. Now, I can't say enough, and I don't specifically say it in the notes here, but water is an essential component. When we talk about acids, it's always in solution, always in solution. It's always dissolved in water, reactions taking place in water. When a hydrogen ion dissolves in water, it forms the hydronium ion. So the hydrogen ion immediately bonds with the water molecule. It's a coordinate covalent bond where hydrogen doesn't have any electrons, and so it forms a coordinate covalent bond with with the oxygen atom to form the hydronium ion. So this is the hydronium ion. Now in chemistry, we use the hydrogen ion and the hydronium ion interchangeably, as if they're the same, exactly the same thing. Although it's the hydronium ion that is the actual species. The hydrogen ion is rarely found isolated or alone. So for simplicity's sake, we almost always just talk about the hydrogen ion, H with a positive charge there. Though in reality, pull back the curtain, it's in fact the hydronium ion. An Arrhenius base is any compound that releases a hydroxide ion, OH, with a -1 charge, when dissolved in water. Basic compounds are also called alkali or alkaline because those metals readily produce the hydroxide ion when added to water. So for example, group 1, remember group 1 are alkali metals. So potassium is an alkali metal. When you put it into water, it will produce hydrogen gas and form potassium hydroxide. Now, potassium hydroxide is aqueous, meaning that you have potassium ions and hydroxide ions. So it's alkali, they're referred to as alkali because when you put an alkali metal into water, it produces hydroxide ion. Same thing for alkaline earth metals, group 2, calcium is an alkaline earth metal. We would also form hydrogen gas and a ionic compound containing the hydroxide ion. So the terms basic, alkali, and alkaline are quite often just used interchangeably. Something will be referred to as being alkaline or having alkali properties or being basic. They're all, for all intents and purposes, the same thing. You're probably most familiar with the term alkaline in regards to batteries, alkaline batteries. And that's because batteries have a very, very thick paste that's basic if you crack open a battery. However, the Arrhenius definition cannot explain why some compounds without hydroxide have the properties of a base. So for example, ammonia. Ammonia is a base, but there's no hydroxide. So how can it be a base? We know it's a base for various ways we can test it, but one of the things that's really easy to do is if we were to put drops of an indicator called phenolphthalein into a test tube that had ammonia in it, it would turn pink. And only a base will do that. So the Arrhenius definition that something that's basic produces the hydroxide ion isn't sufficient. It doesn't explain how ammonia and other compounds can behave as a base even though they don't have the hydroxide ion. So we needed a broader definition that would explain why some compounds that don't have hydroxide are basic. Enter in Johannes Bronsted, who is Danish, and Thomas Lowry, who was British. And in 1923, they proposed what we now refer to as the Bronsted-Lowry definition. However, both of these scientists worked individually and came up with this idea, this theory, independently. And so it's named in their honor. Every now and then you'll have that happen where scientists are, they collaborate around the world, share data and everything, and kind of working on similar things, and they come up with the same ideas about exactly the same time. And so to credit both of them, in this case, it's named Bronsted-Lowry. Okay, and their definition is an acid is a proton donor, and a base is a proton acceptor. Okay, now what do we mean by proton? Well, where did that come from? Well, note, a proton is just another name for a hydrogen ion. This would be a hydrogen atom. Remember, a hydrogen atom just has a proton and an electron. Almost all hydrogen atoms have no neutrons. And so this is the most common, 99.99% of all hydrogen atoms is this. So if we got rid of the electron, well, we would have just the proton. And if we got rid of the electron, of course, we would have the hydrogen ion. So the hydrogen ion and a proton are exactly the same thing. The Bronsted-Lowry definition explains why substances like ammonia that we saw a few minutes ago are basic. And the key to this is the interaction of the compound with water. So when we look at this reaction, we can see that the water donates a hydrogen ion, or what we better said, donates a proton. And we can tell that because after the reaction has taken place, we have the hydroxide ion. And the ammonia, before the reaction takes place, is just NH3, no charge on it. Afterwards, it's NH4 with a positive 1 charge. It has accepted a proton. So the water is our acid. It donated a proton donor. And the ammonia is a base. It was a proton acceptor. Now, to do this, you have to look on both sides of the equation. You can't just look at a compound and tell that it's going to behave as an acid or a base. We have to see what transpired in the reaction. So look on both sides. So NH3 before, NH4 with a positive 1 afterwards means that it gained a hydrogen ion or a proton. Water, H2O, now just OH with a negative charge, it lost a proton or a hydrogen ion. So the hydroxide, rather than the Arrhenius definition was that a compound that contains hydroxide, but in the Bronsted-Lowry definition, the hydroxide ion comes from the water molecule. So that can explain why a compound, through its interaction with water, is able to produce the hydroxide ion. Not directly, but indirectly. Bronsted-Lowry acids can be monoprotic, meaning that they donate 1 proton, so hydrochloric acid. Diprotic donates 2 protons, so sulfuric acid, an example of that. Or triprotic, and phosphoric acid is an example of that. It gives off 3 protons. Now, a little hint here, hint. In your homework, you're going to be asked to give an example of a monoprotic, diprotic, and triprotic acid that's not used in your notes. So in other words, don't use these 3 that I just gave you. Simply look at other examples that are in the homework, or you could search Google. Just search for monoprotic acids or diprotic acids or triprotic acids, and you'll find it in a second. Conjugate acid-base pairs. Any 2 species that differ by a single proton. Example. So if we were to look at this reaction, now almost all the reactions that we're going to be looking at now will have a double arrow. Not all. When we don't see a double arrow, it's just to kind of make the point that that the reaction, what occurs in the reaction. But many of the acid-base reactions that we'll be referring to will have the double arrows. Okay, now, like I was talking about earlier, we have to look on both sides of the equation to kind of see what was going on here. So we can see that we have, this is called the bicarbonate ion. Afterwards, it's just the carbonate ion. So we can see that it lost a hydrogen, whereas the sulfide ion now is the bisulfide ion. It gained a hydrogen. So the bicarbonate donated a proton. the sulfide ion gained a proton. So the bicarbonate is our acid, and the sulfide ion is our base. And again, we can tell that by seeing what transpired and what we end up with on the other side. Now, the double arrows here, if we were going back in the opposite direction, what is the acid? Well, it would be the bisulfide ion is our bisulfide ion. That is our acid because it donates a proton, and we can tell that going back in the opposite direction because now it's lost the hydrogen that it had. So it's referred to as a conjugate acid. So the conjugate acid is going back in the opposite direction. And the carbonate is called a conjugate base. Now, an acid and its conjugate base, and a base and its conjugate acid, are what we mean when we refer to something as conjugate acid-base pairs. So the bicarbonate and the carbonate are conjugate acid-base pairs, and the sulfide and the bisulfide are conjugate acid-base pairs. So again, go back to the definition here. Any two species that differ by a single proton. And again, it's important, just one proton, one hydrogen ion. So you can see the acid here and its conjugate differ by nothing but one hydrogen ion. And the same thing for the sulfide and the bisulfide differ by a hydrogen ion. Students often kind of get this mixed up and think that the acid and the conjugate acid on the other side are somehow connected. No, the difference between an acid and its conjugate or a base and its conjugate is a hydrogen, and that's it. Now note, it's important to remember that the hydrogen ion has a positive 1 charge. Therefore, the loss or gain of a hydrogen ion is also a loss or a gain of a positive charge. So when the bicarbonate ion lost a hydrogen, it also lost a positive 1 charge. And so afterwards, this was HCO3 with a negative 1 charge, but it's now just CO3 with a negative 2 charge. So it lost the hydrogen and a positive 1. So it went from a negative 1 to a negative 2. Conversely, the hydrogen, or the sulfide, which was a negative 2, gained a hydrogen, and it also gained a positive 1 charge. So now the bisulfide ion has a negative 1 charge. So the positive 1 plus a negative 2 gives us a negative 1. Okay, I know what you want to do. You want to practice. Okay, so identify, and you have homework just like this. Identify and connect the conjugate acid-base pairs in this reaction. All right, so now what you want to do is look on both sides of the reaction, see what lost a hydrogen ion, what gained a hydrogen ion, and label the acid-base, conjugate acid and conjugate base. Why don't you pause the video and see if you can do it yourself, and I will do it in 5, 4, 3, 2, 1. So we can see that the water is our acid. How do we know that? Because afterwards, it's the hydroxide ion. It lost a hydrogen. Whereas, and this is aminoethane, aniline. Oops, I'm sorry, I'm doing this out of order here a little bit. So this is our acid, this is our conjugate base, and this is our base. So we can tell that because we had NH2 here, no charge on it. Afterwards, it's NH3 with a positive 1 charge. So it must have gained a hydrogen or a proton. So this is our base, our conjugate acid, our conjugate base. Connect the pairs. Again, the difference between an acid and its conjugate or a base and its conjugate is a single hydrogen ion. Buffer solutions. So you might ask, well, why do we need to know all that? You probably ask that all the time, but buffer solutions are essential for life as we know it. The pH of your blood is about 7.2 to 7.4. It's a very, very narrow range. If the acidity or basicity of your blood was to go up or down from that, you would be dead. We have what are called buffers in our system, and all living organisms do, such that if we take in acid, it's neutralized. If we take in a base, it's neutralized. And these are called buffer solutions or buffer systems. A buffer solution contains conjugate acid-base pairs that will resist a change in pH. pH is a topic we'll get to in a few days. It's a measure of the acidity or basicity of a solution. 0 to 7 is acidic. 7 to 14 is basic. More on that later. But just keep in mind if you're not already. I think most of you already know that. Know something about that. pH is a measure of acidity or basicity, and so a buffer system really resists changing the pH, meaning that it resists changing, becoming more acidic or more basic. Excuse me. For example, our blood, has a buffer system containing the bicarbonate ion and the carbonate ion. We can easily represent a buffer system by using a slash between the two. And by the way, how does this occur? Well, when we breathe in, carbon dioxide is in the air. So when we breathe in the carbon dioxide dissolves in the water, our blood, and the bicarbonate ion forms. And from that, the carbonate ion forms. And so we have both of these in our blood simply by breathing in carbon dioxide. Okay, so now how does this work? Does this resist a change in pH? And it's pretty slick the way this works. So how does this system work? Well, if we add an acid, so let's say that you drink orange juice. Well, orange juice is a sorbic acid. It contains the hydrogen ions that are released when you drink it. And so you might think that you acidify your body because you're taking in all of this acid, but no. The bicarbonate carbonate buffer system will neutralize that acid. And how does it do it? Well, the hydrogen ion, the proton, will bond with the carbonate ion to form the bicarbonate ion. And so notice the arrows is only going in one direction. And so this reaction would not be reversible or not readily reversible. Okay, so the carbonate neutralized the acid. Now here we're just referring to the acid as being the hydrogen ion because, of course, a hydrogen or an acid donates a proton, donates a hydrogen ion. So ultimately, that's what we're interested in when we're talking about an acid. If a base is added, not many foods are basic. Basic foods have a bitter taste to it. Broccoli is basic. So if you ate a bunch of broccoli, you're not going to become all basic because the hydroxide ion will be neutralized. And it's neutralized by the bicarbonate ion. And so the bicarbonate ion donates a hydrogen ion to the hydroxide ion to form water. So the bicarbonate neutralized the base. So to kind of recap here, so we have, this is our buffer system. One of them will have a hydrogen, one of them will not. The one that does not have the hydrogen will react with the acid to neutralize it. And the one that does have the hydrogen will react with the hydroxide ion to neutralize it. Again, I know you want some practice. So show how the biphosphate and phosphate buffer system can neutralize an acid or a base. So what you want to do is, just like I just did, use the hydrogen ion to represent an acid. So how would it react? What would it react with and what would it form? And then the hydroxide ion to represent a base. How would it react with either one of these and what would form? You have a homework problem just like this. So I will do it in 5, 4, 3, 2, 1. Okay, if an acid is added, well, then it's going to bond with the phosphate to form the biphosphate ion. If a base is added, it'll react with the biphosphate ion to form the phosphate ion and water. Amphoteric substances. I'm sorry, not amphoteric, amphiprotic substances. These are substances that can accept or donate a proton. So let's look at these 4 examples. All 4 of these can either donate a proton or accept a proton. Now remember, if it donates a proton, it would be an acid. If it accepts a proton, it would be a base. So if it accepted a proton, it would become the hydronium ion. If it lost a proton, it would become the hydroxide ion. So you might want to pause the video, see if you can complete the other two here. So it's just that easy. The acid, we add a hydrogen. For the base, we remove a hydrogen. I'm incorrectly referring to a hydrogen. I should be saying protons, but trying to be explicit here to help you along. Anyway, so why don't you pause the video, see if you can complete this table, and come back in 5, 4, 3, 2, 1. Okay, so this is the bisulfide ion. So if it gained a hydrogen, it would be hydrosulfuric acid. If it lost a hydrogen, it would be the sulfide ion. And the same here, 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 and here. Now again, remember, when we talk about losing or gaining a hydrogen ion, we have to pay attention to the positive one charge that it carries. So for the bisulfide ion here, when it gained a hydrogen, it also gained a positive one charge. So it no longer has a charge here. And when it lost the hydrogen, it also lost a positive one charge. So it has a -2 charge now. And so these follow that same logic. All right, the last topic, amphoteric substances. This is really a higher level topic. An amphoteric substance is any species that can react as either an acid or a base. Now, you might recall from topic 3, when we looked at the period 3 oxides, we looked at the chemical properties of period 3 oxides when they react with water. And when we got to aluminum oxide, we saw that it was what we called, and you had first seen this term there, amphoteric, meaning that it can behave as an acid or a base. If you go back in your notes, you'll see the two reactions involved. So it's an example of a substance that's amphoteric. Now we can bring in what we just talked about, amphiprotic, because all amphiprotic substances are amphoteric, but not all amphoteric substances are amphiprotic. So what you just need to know is that amphiprotic substances are amphoteric. They behave as either an acid, which is a proton donor, or a base, which is a proton acceptor. But you just need to be aware that there are other substances, like aluminum oxide that we saw in a few units ago, that can behave as either an acid or a base, but not by losing or gaining a proton, as an amphiprotic substance would. The mechanism for it, you'll have to take higher level chemistry or do a little bit of research on your own. Okay, that is it. That is the end of notes.